Hydrocarbons with one or more carbon-carbon double bond are called alkenes, and these are unsaturated since it is possible to fit more hydrogens on to form alkanes. Although when we draw the carbon-carbon double bond, the two bonds look identical, in fact, the two bonds that make up the double bond are different. One of the bonds is formed by direct overlap of orbitals to make a sigma bond. This bond is equivalent to a single carbon-carbon bond. The second bond is formed by sideways overlap of p orbitals above and below the plane of the molecule. This forms the pi bond. The pi bond, because it is formed above and below the plane of the molecule, fixes the groups on each carbon atom in place and prevents rotation. The pi bond is weaker than the sigma bond, and this makes alkenes more reactive than alkanes. The bond angles around each carbon forming the carbon-carbon double bond are 120 degrees, and the shape around each carbon is trigonal planar. This contrasts with alkanes, which have a tetrahedral shape and a bond angle of 109.5 degrees. Just as it is possible to have cyclic alkenes are possible with one of the more common molecules of this type being cyclohexene. Alkenes readily undergo addition reactions since the pi bond is readily attacked by an electrophile. An electrophile being a species that can accept a pair of electrons to form a covalent bond. For example, the mechanism for electrophilic addition of ethene by hydrogen bromide goes like this. The polar nature of the hydrogen bromide means that the hydrogen is electron deficient and can attack the double bond as this is electron rich. The hydrogen to bromide bond breaks and the new bond forms from the carbon to the hydrogen, creating a negatively charged bromide ion and a positively charged carbocation as short-lived intermediates. The negatively charged bromide ion can then form a covalent bond with the carbocation to form the product bromoethane. If this reaction occurs with a molecule that is not symmetrical around the double bond, for example propene, two products are formed, one bromopropane and two bromopropane. By understanding the electrophilic addition mechanism, we will be able to explain why two products are formed. The double bond can spring open this way, leaving the positive charge on carbon number 2, which will then form a bond with the bromide ion. Or it can spring open like this and leave the charge on number 1 carbon, which the bromide ion then joins onto. You can predict the product, which will be the major product, by applying Markovnikov's rule, which states, when a molecule HA adds to an unsymmetrical alkene, the major product is the one in which the hydrogen atom attaches itself to the carbon already carrying the larger number of hydrogens. The specification states that you do not need to know the reasoning behind the Markovnikov rule. However, it may be helpful to know that this happens because the carbocation, that is the most stable, produces the most abundant product. Alkyl groups donate negative charge by something called the inductive effect, and so the intermediate with the carbon carrying the positive charge with the most alkyl groups attached will be the most stable, and so will be the intermediate that will produce the most abundant product. Electrophilic addition reactions can also take place with bromine as the electrophile. Although there is no permanent dipole across the bromine molecule, the high electron density of the double bond induces a dipole, and then it behaves in the same manner as hydrogen bromide. There are a number of addition reactions you need to learn. Reaction with bromine or other halogen to produce a dibromo or dihalogeno compound, with hydrogen bromide or other hydrogen halide compound to produce monosubstituted products, with hydrogen, which requires a temperature of 150 degrees C and a nickel catalyst to produce alkanes. This is the reaction used to produce margarine, and with steam with phosphoric acid catalyst under high temperature and high pressure to produce alcohols.